Hi everybody, good morning, and I hope you have a nice day today, and I hope you have enjoyed our summer school until today. So today we will have a talk from Professor Zubin Gharamani, University of Cambridge, and Chief Scientist of Uber. His title of talk is the title of his talk is Probabilistic Machine Learning and AI. Zubin Gharamani is Professor of Information Engineering at the University of Cambridge and Chief Scientist and VP of Artificial Intelligence at Uber Technologies Inc. He studied at the University of Pennsylvania, received his PhD from MIT, and was a postdoctoral fellow at the University of Toronto. He moved to the UK in 1998 as one of the founding faculty members of the Gatsby Computational Neuroscience Unit at UCL, and he held a concurrent faculty appointment in the machine learning department at Carnegie Mellon University for 10 years. He was the first Cambridge director of Alan Turing Institute, the UK National Institute for Data Science and AI, and he co-founded Geometric Intelligence, an AI startup which was acquired by Uber and became the nucleus of Uber AI organization. Zubin is also currently Deputy Director of the Leverhulme Center for the Future of Intelligence, studying the impact of AI on society, and a Fellow of St. John's College, Cambridge. Zubin is known for his pioneering work on probabilistic approaches to machine learning and artificial intelligence, and he has published over 300 research papers on these topics, as well as mentoring 76 PhD students and postdocs. In 2015, he was elected as a Fellow of the Royal Society for his contributions to machine learning. So we are going to yeah, start broadcasting his talk now, and I hope you enjoy it.
Hi, I'm Zubin Gharamani, and I'm delighted to have been invited to the 4th IPM Advanced School on Computing for Artificial Intelligence. Today I'm going to be speaking about probabilistic machine learning and AI, and I wanted to start out by thanking the organizers for inviting me. I'm going to now share my screen. So hopefully you can see my presentation. And I'll start. So as I said, I'm going to be talking about probabilistic machine learning and AI. I work both at Uber and at the University of Cambridge. So to start out with, there are many related areas. So this school is on artificial intelligence, but people often use the term machine learning. I'll generally use the term machine learning. It's very closely related to computational statistics. Fields like data science are closely related, data analytics, data mining, even areas like adaptive control deal with some of the same topics. And of course, neural networks and deep learning are closely related areas. Now, I don't want people to get confused about all of the different terminology. These areas are related to each other in an interesting way. I'll spend a couple of minutes just talking about one way of thinking about how these fields are related. This is borrowing an image from my colleague at Cambridge, Richard Turner. And so what you can see in this image is on the left-hand side of this image are theoretical foundations. And so the mathematics of data analysis is statistics, so that is at the core of the theoretical foundations. But also machine learning, signal processing, sub areas of machine learning like deep learning are parts of the theoretical foundations. And then on the right side of this image, what you see are downstream application areas. So, you know, when people try to apply these types of methods to extracting value and knowledge from data, that's often called data science or data mining. But when people try to apply these methods to recreating intelligent behavior, that's sometimes called AI or machine intelligence. But these areas are all very, very closely related. There's just kind of one big mess of related topics. What the topics have in common is a few key ingredients. All of the areas I talked about use data to build models and make predictions, decisions, and develop understanding from that data. So it's data-driven predictions, decisions, and understanding. That's really what they all have in common. And it's been an incredibly exciting time for AI and machine learning. It's been exciting because there have been many breakthroughs in AI and games. For example, famously, the breakthroughs in Atari, the game of Go by companies like DeepMind, breakthroughs in poker, in chess, and many other such games. But it's also been incredibly exciting, not just because of these breakthroughs in games, but because AI and machine learning are being applied to a huge number of different practical areas. All current speech and language technologies are based on AI and machine learning. Computer vision methods are based on AI and machine learning. A lot of scientific data analysis is now moving towards using algorithms and ML methods to help analyze large amounts of data. Recommender systems that we're all familiar with are based on AI and machine learning. Self-driving cars, which are becoming more and more of a reality, of course, and financial prediction, automated trading. And these are just 6 areas I could fit on one slide. I could have made many slides of industries or societal areas that have been impacted by machine learning. Well, one of the most exciting developments in AI and machine learning is deep learning. And many of the breakthroughs you've heard about are driven by advances in deep learning. So I want to spend a few minutes just giving some context on what is deep learning and what are its limitations, because I think it's important to understand the limits of deep learning as well. So deep learning is basically a rebranding of a rather old idea in AI, which is called neural networks. And neural networks are just simply tunable nonlinear functions with many parameters. So here I've shown an image of a neural network. It takes in some inputs X, it produces some outputs Y. So it's learning a mapping or function from X to Y. And the parameters of that neural network are called the weights of the neural network. And in statistics, we often use theta to denote the parameters. So think of theta as the parameters of the model, sorry. Now, a multi-layer neural network model simply computes the overall function from X to Y as a composition of functions, where each function is one of the layers in the neural network. So here what you see is an example of a one hidden layer or a 2-layer function that maps from X to Y through a linear combination, and then a nonlinearity, and then another linear combination, and then some noise added at the end. So this is a simple 2-layer neural net. And of course, nowadays, neural networks can be much deeper than 2 layers. Now, neural networks are usually trained to minimize some error, and the errors almost always correspond to some form of a log likelihood. So essentially, neural networks maximize log likelihood or log penalized likelihood using some variation on stochastic gradient descent optimization. So maximization of likelihoods is a nearly 100-year-old idea in statistics. And stochastic gradient descent is also a very old idea in optimization theory. So when you boil it down to its essence, a neural network is just a nonlinear function combined with a little bit of very basic statistics and a little bit of basic optimization. So why is it exciting then? What's the big deal if that's all that it is? Well, modern neural networks or deep learning models are simply neural networks very similar to those that were popular in the 1980s and 1990s with a few innovations. So the image I'm showing here is a deep learning network, which takes, for example, an image that would be the input X, and it produces output predictions, which are potential labels for objects that might be in the image. Okay, it's still a function from image pixels to labels. What's different from the old neural nets of the 80s and 90s? Well, there have been some architectural and algorithmic innovations. For example, we now know how to deal with many layers. We have better activation functions such as ReLUs. We have regularization methods such as dropout, etc. So there have been a few interesting ideas since the 80s and 90s. We have vastly larger data sets, web scale data sets to train these networks on. The data sets from the 80s and 90s were tiny. We also have vastly larger compute resources, GPUs, TPUs, IPUs, cloud computing, really orders of magnitude more compute resources than we had in the past. We have much better software than we had. So now, rather than having to code everything yourself, there are many, many open source frameworks for learning your deep learning architectures and parameters from data. So you can even learn models, you can do machine learning without actually having to know any calculus. In fact, one of my children actually took a class on machine learning, and she's only 10 years old, and she was training deep learning architectures. So it's possible to do that without really knowing any math with modern software. And finally, we have vastly increased industry investment and media hype that has led to many, many more people in the field of machine learning. So deep learning has been wildly successful, and there are thousands of papers in the field. So it's sometimes mind-boggling to kind of figure out what's important and what's not. And for me, there are 7 key ingredients, key ideas that have made for the success of deep learning. So this is my personal view. This is a summary of many, many papers in the field of deep learning. And so the first thing I would like to highlight is that very large models can work very well. This is an idea that seems contrary to a lot of classical statistical thinking. So training statistical models with millions, tens of millions, or hundreds of millions of parameters on relatively limited data sets seemed like a crazy idea. But actually, there is even a branch of statistics that is closely related to this, which is non-parametric statistics. And I'll talk about this a little bit later. In non-parametric statistics, what we consider are the limit of statistical models where you have infinitely many parameters. And so in a sense, modern deep learning with its tens and hundreds of millions of parameters is successful because the models are very, very flexible, just as they are in classical non-parametric statistics. Of course, if you have a model with millions of parameters, but you have a small data set, it's not going to learn very well. And so hand in hand with the large size of the models is the fact that we use much larger data sets, orders of magnitude larger data sets. And in some scenarios, for example, reinforcement learning, what we're using is large amounts of simulated data. So it doesn't even have to be real data. So very large models, very large data sets. A third idea I want to highlight is the usefulness of automatic differentiation and software to do it for you. So rather than an error-prone approach to taking derivatives by hand and then coding them in software, you let the computer do that, which is great. A fourth idea that has repeated many times in the field of deep learning is that if you want to make your model deep, whether it's deep in layers or deep in terms of ability to capture information over time, then it's useful for every layer of operation to stay close to the identity function. Trivially, if you take the identity function and you compose it with itself 100 times, you still get the identity function. But if you stay close to the identity function, then each layer of operation can actually do a limited amount of work. And that means that you can combine tens or even hundreds of layers into your neural network to get the mapping from inputs to outputs without your gradients either exploding or vanishing, which makes learning very problematic. So staying close to identity makes it possible to have deeper networks, and it makes it possible to learn those deeper networks through gradient-based methods. Fifth idea I want to highlight is that stochastic optimization works surprisingly well. And so, I'm talking here about SGD and also its adaptive variance. And, there are many, we could spend an hour talking about the many reasons why this might be the case. One of the hypotheses is actually that stochastic optimization, through the noise that is introduced by randomly subsampling many batches of data, through that noise, you actually get smoother error surfaces, and it's easier to escape local optima and to find better optima of your objective function, as well as avoiding really bad forms of overfitting. The next idea is that better initialization matters. So if you try to initialize a 10 or 100 layer network, if you do it poorly without thinking about the properties of the network, it won't learn at all. If you do it well, it can learn very well. And then the last idea I want to highlight is the idea of parameter tying or symmetry. This is a very old idea that has been around since the early days of statistics, certainly since the hidden Markov model of the 1960s. And this idea is that you want to replicate parameters in different parts of the model to capture certain properties that you assume about your data. So I would imagine like an idea like convolution is an example of parameter tying and symmetry, recurrent networks, recursive networks, and all other sorts of networks have these structures in them. So now deep learning Deep learning has been wildly successful, and it gives amazing performance on many benchmark data sets, but it's not magic. And it has some pretty important limitations. First of all, deep learning tends to be very data hungry. Often you need millions of examples to train. And in some machine learning problems, you don't have millions of examples. Second, it's very compute intensive to train and deploy, which can be quite limiting. Deep learning methods are easily fooled by adversarial examples. I'll show a picture of that if you haven't seen it. They're finicky to optimize. The optimization function is non-convex. The choice of architecture, learning procedure, and initialization, it's all quite a bit of a pain. They're uninterpretable black boxes, lacking in transparency and difficult to trust. It's non-trivial to incorporate prior knowledge and symbolic representations, and they're very poor at representing uncertainty and extrapolating to new data sets. So there are many limitations of deep learning. And of course, there are many, many researchers working on all of these limitations. So the field is clearly advancing on all of these dimensions. Now, to just go over the point about being easily fooled by adversarial examples, here's an image of a school bus and an image of a dog. These are correctly classified by the deep learning architecture. If you add a tiny amount of carefully chosen pixel perturbations to these images, then the image that you get here is classified as an ostrich very confidently. And again, the image that you get here on the bottom row is also classified as an ostrich very confidently. And in fact, if you choose your pixel perturbation carefully, you are able to get the deep learning architecture to tell you that the image is almost anything that you want. So the pattern of mistakes that the deep architecture makes is counterintuitive. It's very different than the types of mistakes that humans make. And it really shows that these methods are quite brittle to the detailed structure of the inputs that you give them. Now, for the rest of this talk, what I want to do is go beyond deep learning. So I want to talk about kind of frontiers of machine learning and AI. And in particular, I'm going to be taking a perspective of thinking about machine learning as probabilistic modeling. So in particular, what do I mean by probabilistic modeling? Well, a model describes data that one could observe from a system. That term model is used in many different fields, from statistics to economics to physics, engineering, social sciences, biology. The term model is used almost everywhere. But in particular, when people say model, they usually mean something, some sort of hypothesis that makes predictions about observable data. That's really important, because otherwise you don't know whether your model is good or not good. Now, if we use the mathematics of probability theory to express all forms of uncertainty and noise associated with our model, then we can continue using probability theory in the form of what used to be called inverse probability, or Bayes' rule, to infer unknown quantities, adapt our models, make predictions, and learn from data. So all we need is a model, some data, and probability theory. Like, that's abstractly all we need. Certainly to do modeling, obviously we need to implement it on a computer and run an algorithm and so on and so forth. And then we also need decision theory. I left out decision theory, but once we have a model, we may want to make some sort of optimal decision. So we need a loss function and decision theory to make some sort of optimal decision if we're building a system that makes automated decisions. So it's a very simple framework, actually. And we can think of almost all of modeling and machine learning with this lens. So let me be more specific. The probabilistic modeling framework for machine learning is based on Bayes' rule. And Bayes' rule is written here with an image of Reverend Thomas Bayes from the 1700s. And Bayes' rule is essentially a simple mathematical theorem for how to update your knowledge when you get data. Or rather, it's phrased in terms of probabilities, updating probabilities in light of data. And I'll walk you through it right now. So before we observe data, we meaning humans or our computer or AI system, whatever it is, there are certain models or hypotheses. And we represent our state of knowledge around those models or hypotheses by defining a probability distribution over those models or hypotheses, including over the parameters of those models. And this is called the prior, okay? Now, every model gives a probability to the observed data. So if it's a well-defined probabilistic model, it's possible to compute the probability of the data given that hypothesis. If it's not possible to compute that, then the model is underspecified. In other words, the model is not a valid model in terms of being able to predict data. It leaves out important elements. So well-specified model in this framework can give a probability to the data. Now the prior, let me come back to that because it's important. The prior is meant to capture our state of knowledge, and there isn't any correct prior. It's just a representation of the possibilities we are willing to consider. So if we are not sure, then we should spread our probability mass over a large space of possible hypotheses. If we're really sure about something, we can concentrate our mass on a smaller number of hypotheses. So once we have the prior and the second term, which is called the likelihood, we multiply these and we renormalize by summing over all the hypotheses that we've considered. This is just a normalization constant. And from that, what we get is the posterior over hypotheses given the data. That's our new state of knowledge after having observed the data. Now, Bayes' rule that is written right here tells us how to do inference about hypotheses from data. And I want to be clear what I mean by hypothesis and data. So data is anything that is measured, and hypothesis is everything else. So we're going to assume that everything else, anything that we're uncertain about, we can use a probability distribution to represent our uncertainty. I also don't like the term randomness, because randomness implies some sort of like process that's random in the sort of sense that like rolling a die might be random. I prefer to use the term uncertainty because there are many things that are not random that we may be uncertain about, right? Like, for example, I'm uncertain about what is the mass of planet Earth. I just don't remember it. So I can represent a probability distribution over what that is to capture my uncertainty. And it doesn't mean it's a random quantity. Now, learning and prediction can be seen as forms of inference using this equation. So in Bayesian machine learning, things are actually rather straightforward. So everything starts from two simple rules, the sum rule and the product rule. So in fact, Bayes' rule itself derives from the sum rule and the product rule written at the top of this slide. So learning, which usually involves learning parameters from data, can be expressed as this equation here, Bayes' rule from the previous slide, where I've simply substituted D for the data that you observe, theta for the parameters of the model that you're trying to infer from the data, M for the model class that you're assuming. Maybe it's the structure of a neural network, or the definition of your decision tree, or whatever it is. And what we have is the prior representing our range of parameters that we're willing to consider as a probability distribution. And then by multiplying it by the likelihood, we get the posterior over parameters. So note that in Bayesian machine learning, there is no optimization rule. You're not optimizing the likelihood or marginal likelihood or anything like that. You're actually simply doing Bayes' rule. Now, if you want to do prediction, then you simply also follow the sum rule of the product rule. And so if you're predicting any unknown quantity X, given the data and your model class, then you integrate or sum over all possible parameter values, the prediction for each parameter value, weighted by this posterior probability that we computed in the previous equation. And so there's nothing arbitrary about this. It just follows from the sum rule and the product rule. And then if we want to do model comparison, if we want to compare two different models for a particular data set, then we simply apply Bayes' rule at the level of models. And this term here, this marginal likelihood term, that I've shown in red, is a very interesting term, and I want to spend a couple of slides just talking about this term. So here is a classical problem in machine learning and statistics. And this problem is, given a particular data set, how do we find a model for that data that neither overfits nor underfits that data? So in this toy example, what I'm showing is 8 data points. These are these red dots. And I'm trying to fit a function, so some mapping from inputs X to outputs Y, to these 8 data points. And the blue line shows a maximum likelihood polynomial fit for the constant, linear, quadratic, cubic, etc., up to 7th order polynomial. And what you can see is that a constant function might be a good model for this. Linear maybe a little bit better. Quadratic seems to fit the data quite well. Then when you go up to 7th order, what you find is that you can fit these 8 data points perfectly, but you're predicting crazy things between these data points. So these wild curves look like you are overfitting terribly. And so we want to avoid both overfitting, what's happening here, and underfitting, what's happening at the constant polynomial, let's say. Now, Bayesian Occam's razor is the idea that we can use the marginal likelihood, which was the term in red on the previous slide here, to avoid both overfitting and underfitting, to in fact do a principled form of model comparison. So if I compute the marginal likelihood for these different polynomials, and that involves not just fitting the polynomial, but actually integrating over all polynomials of a particular order, which is actually straightforward to do analytically if you choose certain priors for your parameters, then what you get is a marginal likelihood curve that looks as follows. It looks like this. So you have here is that the marginal likelihood tells you 0th, 1st, 2nd, and 3rd order seem quite reasonable. Higher order than that is very, very low marginal likelihood. You can't even see it on this plot. Second order seems to be the best. And if I were to change my priors, this shape of this curve would change a bit, which is unsurprising. It needs to change because different priors are different assumptions. But the basic principle that you can avoid both underfitting and overfitting is well captured by the marginal likelihood. Now, conceptually, this is the way to think about it. So if I'm comparing model classes, say M and M prime, I can use Bayes' rule to compare model classes, which I've shown here. The marginal likelihood, I've written out the expression for the marginal likelihood here. This is just following from the sum rule and the product rule I had 2 slides ago, written as an integral. And the marginal likelihood, I can read this equation in these 3 following ways. So this is just me saying in words what this equation means. The marginal likelihood is the probability of the data under the model averaging over all possible parameter values. So it's not choosing the best parameter value for every model class. It's actually integrating or averaging over models of parameter values. The second way to read this is that it's the probability that randomly selected parameters from the prior would have generated a data set D. And when you have a more complex model, then randomly generated parameter values will give you lower probability for any one particular data set, just because more complex models spread their probability mass over a larger space of possible data sets. And if you like information theory, log base 2 of 1 over the marginal likelihood is the number of bits of surprise at observing data set D under model M, where surprise is defined in information theory, where entropy is the average surprise in this case. And that's very intuitive because it's saying if you want to do model selection, choose the model that is for which the data is less surprising. So in this case, what the marginal likelihood is saying is that for this particular data, it would be quite surprising to observe it as a 7th order polynomial, but it's not very surprising for this data to have come from a 2nd order or quadratic polynomial. So deep learning has been incredibly successful, and not a lot of deep learning talks about probabilistic machine learning and AI. And so an important question to ask ourselves is, why do probabilities matter for AI? Can we just brute force our way by throwing bigger data sets at bigger models and hoping for the best? So here are a few reasons why I think probabilities still matter and continue to matter for AI, even if, even possibly are mattering more and more for AI than they did in the past. So first of all, calibrated models and prediction uncertainty are incredibly important. When you go from the realm of predicting, whether an image is a cat or a dog, to the realm of like building a self-driving car or a medical diagnosis system, you really need to have systems that know when they don't know. So you need systems that express their uncertainty so you can make good decisions based on the outputs of the system. If the uncertainties are not calibrated, the results can be disastrous and even deadly. The second reason why probabilities matter for AI is, as I showed you in the previous slide, using Bayesian Occam's razor, we can actually get the computer to do complexity control and structure learning. So we don't really need to invoke ad hoc principles for figuring out what the complexity of the model should be, or how to set regularization parameters, or all of these other things that people seem to obsess over these days. Uncertainty is in particular very important for active learning and for black box optimization, for reinforcement learning, and for any place where your AI system has to do a trade-off between exploration and exploitation. And the reason for that is that the fundamental notion of exploration is that you need to know how uncertain you are about something to figure out whether you should be exploring there or not. And so the whole field of active learning and black box optimization could not work if we didn't have uncertainties. Similarly, most advances in reinforcement learning are based on predicting uncertain outcomes of the actions that you're taking now and trying to optimize for that. So we really need systems that make rational decisions. And this is also an important topic because, if we want to build AI, we have to have a theory of what is rational decision making. And in fact, Bayesian inference is the foundation for rational decision making under uncertainty from a sort of broadly accepted philosophical perspective, although sometimes there are camps that try to come up with other frameworks for rational decision making, but probability theory for many reasons is inescapable for rationality. The next point I wanted to make is that probabilities matter as a way of building prior knowledge into learning systems. So we want to be able to use the knowledge that we have to get learning to be better and faster. We want to make sure that the knowledge is updated in a coherent way and in a robust way as you get more data. So we don't want arbitrary, weird things happening as you get more data. We want to converge onto something sensible as we get more data. And finally, we need to make sure that our learning algorithms work on both small and large data sets. And although many advances in AI have happened because of very large data sets, small data sets are very important too. And in fact, many large data sets are actually large collections of very small data sets. So for example, a particular patient might have a very small number of measurements about him or her in a medical database. The medical database might be very large, but for that particular patient, there is a small amount of information that we need to be able to leverage in the context of this larger amount of extra information that we have from other patients. Great. So I'm going to pause there. In this part of the talk, I want to move from the background tutorial material to some current and future research directions, some areas that I think are particularly exciting. Great, so I'm just going to continue from where I was before. One way of thinking about the areas that I find exciting for research is that they all tie together in this common theme of automating machine learning. So essentially, many of the areas that I'm going to cover involve taking machine learning, which is already about learning automated models from data, but further automating it so that some aspects of like the arbitrariness of like human decision making are removed, and things operate more efficiently and more easily. So I'm going to cover a few of these areas. I'm going to talk about Bayesian deep learning, Bayesian optimization, probabilistic programming, the automatic statistician. I'm going to cover these very briefly. I'll give some references so people can follow up on these topics if they want to at a later stage. So Bayesian deep learning. Now, remember, deep learning is just about learning neural networks from data. And neural networks are just statistical models with some parameters, the weights of the neural net in particular. And I want people to very clearly separate out in their minds models and methods. Okay, so neural network is a model, and decision trees are another class of models, and mixture models are another class of models, graphical models are a class of models. There are many different kinds of models. Methods are algorithms that are used for learning models from data. So stochastic gradient descent is a method, convex optimization is a method, Markov chain Monte Carlo is a method. And so broadly speaking, we can mix and match models and methods. So neural network or deep learning architecture is a model. And what we're talking about when we refer to Bayesian deep learning is the application of Bayesian methods to neural network models. So as such, the idea is very straightforward. A neural network has some parameters, theta, and what we need to do is before observing the data, we put a prior on the parameters that represents a range of possible parameter values that might be reasonable for a neural network. And then as we learn from data, we update that prior to obtain a posterior distribution over the parameters given data, which is in this second line here. And in this notation here, the alpha are these things called hyperparameters, which just represent things like the width of the prior and so on. So Bayesian neural networks just involves applying Bayes' rule to the parameters of a neural network. In theory, this is super straightforward. In practice, it's a little bit more complicated because you need to figure out how to apply Bayes' rule to these parameters. How do you represent probability distributions over parameters of a neural network? And there are many, many different classes of methods that can be used for this, from Markov chain Monte Carlo methods to variational methods to basic forms of particle filtering. Even maximum likelihood can be seen as an approximation to the Bayesian method. A really interesting fact about neural networks is that they're closely related to a model known as a Gaussian process that's been around for about 100 years. A neural network with one hidden layer, when you take the limit of infinitely many hidden units, making the network very, very wide, and if you put Gaussian priors on the weights, it also works for some other kinds of distributions. In that limit, it converges to a Gaussian process. And this is an image here at the bottom of a function approximation given by a Gaussian process. And this was a result that Radford Neal developed in his PhD thesis in the early 90s. And this link between neural networks and Gaussian processes is both beautiful and also practically very, very important. In fact, the results from Radford Neal's work in 1994 continue to be developed. And so there are now a number of papers looking at the relationship between wide neural networks and Gaussian processes, but also wide and deep neural networks. So in some recent work that we did, we actually looked at what happens when you have a deep neural network, but if each of the hidden layers is actually quite wide. So when each of the hidden layers is quite wide, then actually every layer of this neural net ends up still being equivalent to a Gaussian process. And theoretically, the whole thing still converges to having Gaussian process behavior. Even in practice, what this figure here shows from the paper is that the predictions made by Bayesian neural network, here the dots are the data points, and we're learning a function from inputs to outputs. The predictions from the Bayesian neural network, if we're doing averaging over the parameters, are virtually identical to the predictions of a Gaussian process. So this is just a practical representation of the theoretical result. The dotted lines, importantly, are uncertainties, and it has the nice property here that as we go away from our training data, our uncertainties explode, which is a really, really good property to have. This is, in this case, both the Bayesian deep network and the Gaussian process know that they don't know what the function is far away from the training data. Now, I talked about Gaussian processes, and I want to spend one slide at least defining what a Gaussian process is, because it is such a fundamental concept in machine learning. So consider the problem of nonlinear regression. So you're trying to learn a function a function f that maps from some inputs x to some outputs y from data, which are these purple dots. Now, when you learn a function from data, you may be interested in the function itself, but you might also be interested in the uncertainty or error bars around that function for prediction purposes. A neural network is simply a parameterization of functions like that. I mean, of course, y could be not continuous, but it could be categorical, like a class label. But for our purposes, that's irrelevant. We can handle that as well. So many models in machine learning are just functions. And Gaussian processes are a way of defining distributions directly on the space of functions. So we can write down P of F with a slight abuse of notations, because functions are infinite dimensional objects, but let's not worry about that. We can write down P of F as a probability distribution over functions, and then just say, well, let's do Bayesian inference in the space of functions. So we have a prior over functions, we observe a likelihood, and then from that we compute the posterior over functions given data. So how is a Gaussian process a distribution over functions? Well, you have, if you remember your Gaussian distribution, a univariate Gaussian distribution is that familiar bell-shaped curve. A bivariate Gaussian distribution is over two variables. A multivariate Gaussian distribution is over n variables. A Gaussian process is the extension of the multivariate Gaussian distribution over infinitely many variables. And in fact, what those variables are points along the line. So I could think of a function. Imagine discretizing a function. Think of it as a very, very long vector, and then imagine a Gaussian distribution over those vectors. So as a definition, P of F is a Gaussian process if for any finite subset x1 through xn of input locations, the marginal distribution over that subset is multivariate Gaussian. And Gaussian processes can be used for regression, classification, ranking, dimensionality reduction, a whole number of interesting things. Now, if you're familiar with models like linear regression, logistic regression, and support vector machines, then Gaussian processes have a very beautiful and deep relationship to these models. So we can start with linear regression, the mother of all, classical supervised learning. And then we can think of applying several operations to linear regression. So one operation is to turn from a regression model, which outputs a continuous variable, to a classification model. Like, for example, where the output is a discrete label. So this is these magenta lines. So if you go from linear regression to a linear classification model, you get models like logistic regression as an example. The blue lines correspond to taking a linear model, and instead of optimizing the parameters of that linear model, what we're going to do is integrate over the parameters of that model using Bayesian methods. So if you follow the blue line from linear regression, you get to Bayesian linear regression. And the orange lines involve taking a linear model and mapping from the inputs to some high dimensional, potentially infinite dimensional feature space, and then doing the linear model in that feature space. So when you do that to linear regression, what you get is kernel regression. Okay, so now if we apply the magenta, blue, and orange lines operations to various different models, we can get from linear regression to kernel regression to kernel classification. So support vector machines live here in kernel classification. We can get to from linear regression to Bayesian linear regression to Gaussian process regression. That's just kernelized Bayesian linear regression. And we can get to Gaussian process, classification, which is kernelized Bayesian linear classification. Now, all this is very interesting and very beautiful. I love to see the relationships between our different kinds of machine learning models. From a practical perspective, if you're used to doing deep learning either in TensorFlow or in PyTorch, the good news is that there are fantastic Gaussian process libraries, GPFlow for TensorFlow Gaussian processes, and GPyTorch for the PyTorch version. And so you can actually seamlessly learn Gaussian process models and even combine them with deep learning models within your big favorite deep learning frameworks. And these libraries also make it quite scalable to do this. So I talked about Bayesian deep learning as one of the frontiers of research. And I wanted to say that actually Bayesian deep learning is a rather old idea. Remember, deep learning is just a rebranding of neural networks. So if you look at early work on Bayesian inference for neural network models, there is seminal work by David Mackay in 1992 using Laplace approximations. There is work at around the same time by Radford Neal on using Markov chain Monte Carlo methods. And around the same time, Jeff Hinton and Van Camp developed variational approximations to Bayesian inference in deep learning, which is closely related to minimum description length. It's just a reformulation of minimum description length, making sure you're correctly doing the integrals. Now, from that early work, it went quiet actually for almost 20 years. And then there's been a resurgence of work on Bayesian deep learning in the last decade or so. And there are a few examples of this that I've cited here. The literature is actually quite large. I'll talk a little bit about some of our own work in this area, but I want to highlight that the main point of this is that what you want is deep learning models that correctly capture uncertainty when you look at new data points. And you also get automatic regularization of various ways. In fact, over the years, we've organized a NeurIPS workshop on Bayesian deep learning, which has been really, really widely attended with many hundreds of attendees. So I recommend the proceedings of the NeurIPS workshop as well as all the videos associated with that. Here is a picture where I'm trying to capture the key idea that I think is really important. If I take a simple classification problem, like telling apart these blue data points from these orange data points, now almost any classifier is going to do this quite well. So here's a Gaussian process classifier, and it correctly classifies the blue from the orange. What I find really interesting is what happens when you go outside of the range of data that you were trained on. So when I go way out here in this region that's white, what the Gaussian process will tell you is that it doesn't know. So actually, it's really good at representing the fact that it's uncertain where it hasn't observed data in the past. In contrast, in the last panel here, a neural network will also correctly classify the data. Its performance is going to be great. But if you extrapolate, if you go far away from the training data, what you find is that the neural network confidently says that either you're in the orange category and the blue category. And that I find really troubling. So having machine learning models that are not just wrong, but are confidently wrong is really, really problematic. I'd rather have a model that captures this uncertainty. But if you combine Gaussian processes with deep learning methods, then you can have the best of both worlds. So here in the second panel, what we have is a GPDNN. It's a class of hybrid of Gaussian process with deep learning model. And this model actually has pretty good uncertainty away from the training data. A second topic I wanted to talk about around Bayesian deep learning is deep sum product networks. Now, a sum product network is a compact representation of a potentially exponentially large mixture model. So this idea has been around for a bunch of years. And I think it's one of these really amazing but underappreciated ideas. So I wanted to spend a couple of minutes talking about this. And the key insight of some of the recent work I'm going to talk about is to take some product networks and define deep versions of these sum product networks with random architectures that are trainable using classical deep learning methods. So, we really want the advantages of stochastic gradient descent with automatic differentiation, GPU support, in a scalable way. And so the key properties of these deep sum product networks are they're trainable in this way. So they look like deep learning architectures as far as your, deep learning framework is concerned. But they allow for some really, really important other properties. So these models can be used as both generative models and discriminative models. And so that's a really powerful thing that is hard to do in the same model in deep learning architecture. So the same model can be used both for generation and discrimination. Their predicted results are comparable to deep neural networks. So I think there is a lot more potential in terms of applications there, given that the predicted results are very good. They end up with better calibrated uncertainties than deep learning architectures, which was the motivating example that I talked about in the previous two slides. It's possible to evaluate the likelihood for these models. So unlike GANs, where it's not possible to compute the likelihood, here we can compute the likelihood analytically, which is amazingly useful. We can do efficient marginalization and conditioning. So that's related to the previous point. So if we want to compute the marginal of some subset of variables, integrating other variables, then we can do that. And we can deal with missing data and detect outliers in a completely coherent and consistent way. So these are, I think, really, really incredible properties of these deep sum product networks. If you want to learn more about deep sum product networks, here's a link to a paper that I recommend by Robert Pehars. This is a picture of a deep sum product network. Essentially, it starts out with distributions over individual variables. These might be Gaussian or any other univariate or low dimensional distribution. And these are combined via products and sums in multiple layers to, in the end, get a distribution over all of the variables. Here are just some of the results from these papers, if you want to look at them more carefully. So deep sum product networks have high modeling capacity, meaning that we can build complex models out of them like we can with deep learning. They're robust to missing data. So we did a whole bunch of experiments, leaving out data and seeing how the performance fell off. And they can detect outliers and inliers. And again, if you want to learn more, here are two references that are quite recent on these deep sum product networks. Great. The next topic I want to talk about is probabilistic programming. And probabilistic programming deals with the fact that machine learning methods, when we think about them in the context of probabilistic modeling, can be quite hard to implement because probabilistic model development involves writing down a probabilistic model, then deriving inference algorithms, and then coding this stuff up. And that's very error prone. So what we want to do is what automatic differentiation did to the deep learning community. We want to be able to do that same sort of trick to all of probabilistic inference, all of Bayesian inference, which is more than just differentiation. It involves also marginalization, conditioning, integration. These are the sort of things that we need to be able to capture with automated tools. So the solution to this is that we develop probabilistic programming languages. And these are languages for expressing probabilistic models as computer programs that generate data. In other words, think about a model as a simulator for possible data that you could have. And then we want to be able to derive universal inference engines that work for these languages. Sort of the programming language is the front end, and the universal inference engine is the back end. And what the back end does is that it does Bayes rule on computer programs or Bayes rule on simulators. So your simulator can generate data in the forward direction. And then what you want to say is, well, given the actual data that I've observed, conditioned on the actual data that I've observed for this simulator, what is the probability distribution over the parameters of that simulator that are conditioned on the actual data that I've observed, that are coherent with the actual data that I've observed? And that's what the inference engine does. And the remarkable fact about this is that it's possible, in principle, to come up with completely universal inference engines. So any computer program that is written in the probabilistic programming language, and the probabilistic programming language could be a completely general Turing-complete programming language. In principle, we can do inference over that. We can apply Bayes' rule to the computer program. We can kind of run the computer program in reverse in some ways. And in fact, there is a long history of this type of work, going back to Bugs, which was a probabilistic programming language based on Gibbs sampling, developed by the expert systems and statistical computing community. Infer.net, a very important landmark developed by Microsoft Research a decade and a half ago. Blog, Stan, which is very widely used by many different communities, Church, Venture, Anglican, Web People, Edward, Turing, Pyro, etc. So there are a lot. In the probabilistic programming language, in the probabilistic programming
So it was a really, really great, nice talk by Zubin. I really thank him for his nice presentation. Hopefully he's also online with us now and waiting for, yeah. Hi.
Hi.
So thanks so much for your really nice and great, also the topic and presentation. It was really nice for summer school. Unfortunately, on slide number 35, we didn't have any voice recorded on your recorded talk. And some of the users have asked if you can elaborate more on this slide, and because some people have found it interesting, but unfortunately, they didn't have the sound.
Yeah, I'm not sure what happened to the recording. It might have been problems with my microphone when I was recording.
Yeah.
But I'll check the video again. I could try to summarize some of that section very quickly. It's also described in the review paper that I shared, the Nature review paper. I talk about the area of probabilistic programming. And the basic idea in probabilistic programming is to write down a model as a computer program that calls random variables. And so it's a computer program that if you run it multiple times, when it calls the random number generator, it would generate different possible outputs, obviously. And that computer program is a representation of a model or a simulator. It could be a generative model, it could be a discriminative model. Your computer program could actually be, a feed-forward neural network or something like that, or it could be something more complicated like a simulation of a hydroelectric plant or something like that. And the interesting thing about this is once you express your model as a computer program, you can do inference over all of the hidden variables, over the variables you haven't observed directly, using universal inference methods. And so just like we can do automatic differentiation on differentiable programs, we can do automatic Bayes rule on these probabilistic programs. It's a fascinating area. It's an area that we've invested in at Uber, that Google and Facebook have also invested in quite heavily. And it's a very hot area in academic research as well.
Great, thanks. So we've got a bunch of questions right now. So I'm just
Sure.
going to start with a general question from some of my side, and then I will go through the questions from the attendees. So can you explain a little bit more about, for example, what real world projects are you using this, for example, as probabilistic languages you have in over? What are some real world problems that you are solving using these Bayesian models or probabilistic models in over?
Yeah, so we use probabilistic models to model all sorts of behavior.
Right.
So for example, drivers and riders, whether they're going to accept a trip or not under various conditions. Those are stochastic outcomes that depend on lots of variables. So we use probabilistic models for that. We've used Bayesian neural network time series models to model some time series for doing various kinds of forecasting. So we use them in many different places, although, it is, it's hard to get probabilistic models to operate at scale in an industrial setting. You have to have scalable languages, you have to have good frameworks and so on. So a lot of our models are more traditional tree-based models or standard deep learning models.
So I start with the first question. They've asked, to learn a Bayesian deep neural network, we need prior knowledge. So does it mean such a model needs more supervision rather than conventional deep learning ones?
Yeah, that's a good question. Um, if what we mean by supervision here is more labeled data, then actually a Bayesian neural network tends to need less labeled data than a conventional neural network because it's better regularized. It deals with smaller amounts of data better. But supervision can also mean uh, human information that we need to give it. So to get a Bayesian neural net to work well, we need to give it some priors over the parameters that are reasonable. Now, people already do this. They have um, rules of thumb for initializing the parameters of a neural network. This is not the same as a prior, but you are always injecting, anytime you build a model, you are injecting prior knowledge, whether it's in the distribution of initialization or distribution that represents the prior over the parameters. You just have to make sure that the prior over the parameters is sensible, that it defines a reasonable range of possible data sets, that it doesn't kind of create a bias to learning very weird things.
Great, thanks. So we go to the next question from Masa. She has asked that how can we evaluate rational decisions made by probabilistic learning models?
Another great question. So we should actually ask, how can we evaluate rational decisions made by humans as well, or even non-probabilistic machine learning models? So let's think about this. When a model is being used, it usually is being used as part of a decision-making process. And this is true for the thousands of models we have at Uber. They're making decisions that affect, how we match riders and drivers or deliver food and things like that. Now, what does it mean for a decision to be a rational decision? And that's almost a philosophical question. So let me try to answer it. A rational decision should use all the information available to the decision maker, and it should maximize the long-term utility of the decision maker. Or it could be of the system if it's a cooperative system with other agents. So one of the good things about Bayesian decision theory is that it tells you how to incorporate all of the knowledge that you have, both the prior knowledge as well as any information that you gain over time into your decision making. And then you need to combine that with some sort of loss or utility to decide what a rational decision is. And this is true whether we're talking about humans, machines, or animals. An animal making a rational decision about whether to eat this food or not, would depend on the animal's state of knowledge about whether the food might be poisonous or not, right? So that's the framework. It boils down to incorporating all knowledge and having a utility function.
Thanks. So we go to the next question from Ahmad. He has asked that what is the pros and cons of Bayesian optimization if we want to use it for safe reinforcement learning, for example?
Great. So in Bayesian optimization, what we assume is that evaluating the function trying to optimize is expensive. And what that means is if evaluating the function is expensive, then we need to think more. The system, the machine needs to use more computation to decide where to evaluate next. And I'm going to use an analogy, which is maybe relevant for Iran. So think of the function evaluation as trying to find an oil well for petroleum. So digging a probe is expensive. So you do a lot of computation and modeling and thinking before you dig a probe to see if there's oil somewhere or somewhere else. Now, in safe reinforcement learning, we also have situations where we might need to evaluate a system like a robot in the real world. And that could, to evaluate a robot in the real world could cause damage to the robot. It could be expensive. The experiment could take a long time. And so Bayesian optimization is very well suited for that. But if we live in a simulated world, then evaluation is cheap. And so it might not be necessary to do Bayesian optimization. So that's where I see the trade-off. Expensive evaluations are good for Bayesian optimization. Cheap evaluations, you can get away with simpler optimizers.
So we go to the next question. I think I also have this question that, okay. Could you please explain the robustness of Bayesian neural networks? Is such a network more robust against adversarial examples? And somehow why?
Yeah, so the robustness of Bayesian neural networks comes from the fact that you account for the uncertainty in the weights of the neural network. So in a neural network, if you fix all the weights, then the only uncertainty that you have is usually in the output layer of the neural network. Maybe you have a noise model in the output. But if you have a finite amount of data, you can't really be sure about what the weights of the neural network should be. So there's an extra source of uncertainty that most machine learning does not represent correctly. So Bayesian neural network tries to represent the uncertainty in the weights of the neural network, and that makes it more robust in the sense that if you now perturb the input, if you go away from where the system was trained on, the neural network should have error bars or uncertainties that grow wider and wider. Okay, and so that means that it's not that the system gives the right answer, but the system just says, I don't know. Now, for adversarial examples, I've studied this a little bit in some papers. I was hoping that it would make the adversarial example problem go away, but still you can find adversarial examples for Bayesian neural network. It's just that the Bayesian neural network, you need a larger perturbation usually for the adversarial example to have the effect that it has. The real problem with adversarial examples is that if you're trying to learn a function in very high dimensional spaces, there are many different directions that you can perturb and get different values of the function.
Right. Thanks. Next question from Hossein. He has asked, can you please compare neural networks to Bayesian networks? What are the key factors which make NN so better in prediction? What are the main advantages of BNs over NNs? And is there any problem that you think BNs are the best model to use for?
Yeah, great question again. So I think we all know, I mean, probably everybody in this community knows neural networks at this point. So I don't need to explain neural networks. Bayesian networks or graphical models They have several different names: DAGs, graphical models, Bayesian networks. They are representations of joint probability distributions. And they've been very important in the history of machine learning. And I think everybody should also learn about Bayesian networks or graphical models. Now, these two things operate at two different levels. A neural network represents a function, let's say the function from X to Y. And the stuff in the middle, the hidden layers and so on, are not really supposed to matter. You're really just trying to learn the function between X to Y. Now you can manipulate and look at the stuff in the middle, but it's not meant to represent the real world. In a graphical model or Bayesian network, you're trying to represent the relationships between many different variables. So there might be X, Y, Z, W, Q, R, and these are variables usually that represent something in the real world, that means something. And you want to show the statistical dependencies between these variables through a graph structure. So for example, if I want to predict if a tissue in a medical image is cancerous or not, I can think of that as something I could compute with a neural network, from the pixels in the tissue to the label, whether it's cancerous or not. But if I want to understand the relationship between many different variables in a patient, like for example, their age, their gender, whether they smoke or not, whether they have these symptoms and these other symptoms and this disease and that disease, then actually a graphical model is a really good way of representing the relationships between these many different variables. We're not just trying to predict one thing from another, we're trying to represent all of these things jointly. So then we can ask the question, what happens if I give this drug to this patient of this age and this gender who might have this disease, and so on. So actually, Bayesian networks or graphical models are very useful for causal inference as well, understanding the relationships between causes and effects. So I think these operate at two different levels. Bayesian networks are more like a way of doing knowledge representation with uncertainty.
Great, thanks. And the next question from Mohammad Hussein, he has asked that generally the output function space of neural networks are very complex, so it seems ambiguous how one can choose priors on these function spaces. Could you elaborate more on the ways to inject possible prior knowledge into our priors when doing Bayesian deep learning?
Yeah, this is another great question. So many people don't actually start doing anything with Bayesian neural networks because they're worried about choosing the wrong priors, so they don't know how to choose good priors. And actually, I think, like I said before, it's a little bit like the choice of initializations for neural networks. Either you think about it yourself or somebody else thinks about it and you just try something automatic. In Bayesian neural networks, people have often used fairly simple priors, like, Gaussian priors on the weights of the neural network or something like that. And you can evaluate whether a prior is good or not by trying out the prior and then generating functions from the neural network and looking at what those functions mean in terms of input-output behavior in data space. Because the parameters of a neural network don't really mean anything. The only thing that has meaning is data. So you should always evaluate priors by seeing what kind of data would it generate. So that's the general rule of thumb. And there's some best practices for choosing priors. It's also very useful to think about what Gaussian processes do, because Gaussian processes are infinitely wide neural networks. If we understand the priors that lead to Gaussian processes, we can also develop better priors for neural networks.
Thanks. And the next question from Rami, he has asked, I think it's a general question. What's the role of behavioral scientists in Uber and how their work relate to AI?
Yeah, great. So Uber has obviously many algorithms that operate, the technology, but fundamentally Uber interacts with millions of people around the world. And these people are, I'm not talking about the self-driving cars, right? I'm talking about the core of the business. The people are the people who drive on the platform, the drivers, the riders, the eaters, the people who order from restaurants, the couriers, all of these people, the truck drivers for Uber Freight. And so the role of behavioral science is really to understand how we can make our products better match what people want. So we need to understand, for example, what the driver's behaviors might be, how they might prefer different products to each other. We need to analyze changes in the products and how they affect the drivers and riders. We need to understand pricing, what would be the effect of giving somebody an incentive to take 10 rides and get an extra $100. Will they prefer that to a different kind of incentive, and so on?
So, thank you. Go for the next question. Mahsa has asked, what if we go back to the drawing board and think of ways to change the structure of DNNs, maybe by using probabilistic models to get a better representation from data, which won't lead to wrong results with high confidence? Because, it seems like a bug in DNNs that could be fixed somehow, she thinks, actually.
Okay. Yeah, so I think there is a basic bug in DNNs. And, I don't think it's, I'm not the only one to believe that. But one way of thinking about it is when I put an input, okay, here is a easy way of thinking about it. If I train a deep neural network to classify cats versus dogs, images, computer vision images of cats versus dogs, it learns that with very high accuracy. Now, if I give it a picture of a table, or I give it a picture of a truck, it'll still say cat or dog. It'll probably say cat or dog with very high confidence, because as you go away from the training data, the neural network, internal hidden units of the neural network saturate, the ReLUs and all of those. If you use either ReLUs or sigmoids, they saturate. And so the function gets more extreme. And so fundamentally, even if I give it 100 million pictures of cats and dogs, fundamentally, if you test it on data it hasn't seen, the neural net will give confidently wrong answers. And so I call this, actually, it's like the fundamental fallacy of machine learning, that we think that our test data is going to come from the same distribution as our training data. But in many real world settings, when we test them, when we deploy these models, they have totally different things that they're exposed to. And so we need to make sure our systems are robust to those distributional shifts between the training data and the test data. So we can change the structure of deep neural nets to allow for some of that uncertainty. It's something I've thought about. I tried writing a paper about it recently, but we never got really good results. I think it's still worth doing research on that. I think we need to think about the fact that each individual unit in the neural net should have some uncertainty associated with it, although that may be too expensive. An easier way of doing this is to just check that your data point is coming from the same distribution that you trained on before you make a prediction. So that's one way of a cheap way of fixing this problem.
Thank you. The next question, Lina, she has asked, could you please elaborate a little bit more on how the reports are generated in automatic statistics?
Yeah, the reports are generated. It's not very fancy natural language. It's basically taking the representation found by the machine learning algorithm, the representation of the model, and then translating that with some templates into pieces of text that then we put together. So it's really template matching. But because the space of models is very large and complicated, the number of possible reports is infinite, but it's not using a language generation model or anything fancy like that.
Okay. So the next question from Ibrahim, he has asked, I think, okay, there are two questions, I'm not sure. Anyway,
Yeah.
to what extent you think methods of symbolic logic representation of knowledge, for example, dynamic, epistemic logic, and deep learning can be combined given a scalability problem? I think we can first go to this one and then.
Yeah, let me answer the first one. I think this is an interesting area. I tend to think about logic in the context of probabilistic models. So for me, probability theory is the extension of logic to account for uncertainty. And probabilistic programming languages are incredibly expressive. So in fact, with the probabilistic programming language, you can represent logical relationships with unknown or unbounded numbers of entities. You can represent neural networks. In fact, you can represent anything you want that can be written in a Turing-complete programming language. So I think in principle, we could unify these within the framework of probabilistic programming. In practice, it won't be very scalable. That's the big problem. I think the question actually points out the problem that for limited amounts of logical reasoning, we can make them scalable, but for completely universal logical reasoning and deep learning, it's going to be very difficult to make that scalable.
And thanks for the second question is that with regards to automating ML, what is your take on bringing new paradigms into the picture? For example, model-based quantum machine learning, given that we have something called Q-infer, mostly used in quantum computing applications.
So I'm honestly not an expert on quantum machine learning. I think that I'm going to wait and see when it becomes practically relevant. in fact, there are various levels at which one can think about quantum computation as being useful. I mean, there are many different examples of useful forms of quantum computation. One of the things that I think would be very interesting is to see at what point quantum computers could be used to accelerate the computations that we do in machine learning. I would like to see it at the hardware level, actually. I think for the principles, for the software principles, we already have all of the tools that we need for advancing a lot of AI and machine learning.
And the next question from Mohammad Mehdi. He has asked, he said, thank you for your interesting talk. And he has asked that the sum product network seems like a nice framework to model complex real world scenarios. So I was wondering if it could be applicable to the brain's behavior in interpreting stimuli, for example, visual and or surprise. In particular, how much probabilistic approaches have been successful for computational neuroscience?
Yeah, so actually, I used to be a computational neuroscientist. I don't know if people know that, but I spent a lot of time interested in the brain and interested in engineering principles for understanding the brain. There are several levels at which people have tried to understand the brain using machine learning principles. And this is even before deep learning. So one of them is, in fact, the whole history of AI and neuroscience have touched at multiple different parts. And one of the most interesting ways in which AI and machine learning have intersected is, in particular for probabilistic methods, is to understand rational decision making in humans and animals. So if you talk to most cognitive neuroscientists or cognitive scientists, they use probabilistic inference and Bayesian decision theory as their model for optimal behavior, and then they try to test human and animal behavior to see how close we are to the sort of optimum defined by Bayesian decision theory. This is well accepted in cognitive science and neuroscience. There's also another area of neuroscience, in computational neuroscience, where people are trying to see how neurons may be able to represent uncertainty in the perceptual world. So, how does a neuron combine information, or not single neuron, but how does the brain, through neurons and the spiking patterns of neurons, combine information from multiple sources? And we know that the right way to combine information from multiple sources is also using Bayes' rule. Combine it with prior knowledge that we might have because of our experience over time to get inferences. How is that computation done by neurons in the brain? And I have a colleague in Cambridge, his name is Professor Ate Lengiel, whose research is on that topic, as well as Professor Daniel Wolpert, who's now at Columbia University, who has also studied this topic for many decades.
So the next question from Mohammad Hussein, he has said, can we say probabilistic model tries to give representation not in sample level, but in distribution level? Thus, it is different point of view for representation learning.
So there's a couple of things going on here. So first of all, what is representation learning? Now, people use that term a lot, but I think there has never been an actual theory of what a representation is. Like it's, people talk about representation learning. Actually, you have data. We have a good theory of what, function approximation is. We have a good theory for supervised learning, but we don't have a good theory of what a good representation is. We have heuristics. We say, oh, this is a good representation because it matches my intuitions. Or we say, this is a good representation because we can use it to solve these 3 or 4 supervised learning problems, which we're interested in solving. But these are not really theories. So I would say, actually, there is no good theory of representation learning. It's just a term that people use. Now, probabilistic modeling, on the other hand, you can think of there being a theory of probabilistic modeling. What I mean by that is I can tell you very easily if a probabilistic model is good or not. I can't tell you easily if a representation is good because I have to also tell you what's the task I'm trying to solve. But for a probabilistic model, a good probabilistic model should give high probability to new data that you haven't observed yet. That's just the basic idea of a good probabilistic model. An even better probabilistic model could be used for causal inferences about what would happen if you change different inputs to a system and things like that. So it's not, I would say that it's not quite accurate that probabilistic modeling is just having distributions over representations, because we don't even know what a good representation is. A distribution over representations isn't going to help us.
Thank you. The next question from Bobak, he has asked how Bayesian Occam razors can be used for online learning where new measured data might have more complexity.
Yeah, that's an interesting question. So in Bayesian, so first of all, Bayesian online learning is in principle very straightforward. So in Bayesian learning, you have a prior, you see some data, you update the prior, it turns into the posterior distribution. Then if you're doing online learning, that posterior distribution is your next prior for when you see the next bit of data and so on. So the mathematics of Bayesian online learning is beautifully clean. And there is no catastrophic forgetting, none of that stuff, none of that stuff bothers you if you do Bayes' rule properly along the way. Now, for Bayesian online learning, sorry, can you show me the question again? Yeah, okay, so for Bayesian Occam's razor, what we're trying to do is trying to come up with a simple model given the data that we have. That's the kind of principle of Occam's razor. Not too simple, not too complicated, just the right size model. But if we get new data, and the new data is from a more complex process, then we should be able to update our model to be a more complex model to account for that. So when we have a distribution over models, we shouldn't really select a model. We should still keep the weights on the more complex models, because as we get more data, we may want to switch from a simpler model to a more complex model. So as you do Bayesian Occam's razor, you start out with simple models, most of your probability on a simple model. As you get more data, you start transitioning to more and more complex models over time. If your data really came from a simple process, you would stay fixed at some point. Otherwise, you would grow into more and more complex models, which for people who are interested is the reason many Bayesians build non-parametric models, which actually have infinitely many parameters.
Okay, and next and actually final question I'm going to ask, because there's a bunch of other questions, but we are out of time. It's
Yeah.
from Mariam. She has asked, how about modifying and improving the prior knowledge and probability distribution in a dynamic and continuous decision process?
Yeah. So this is very reasonable. I mean, the way there is no single prior. The way we think about a prior is simply prior to whatever data that we've observed. So essentially, if you think about lifelong learning, we're all born, we have some prior that's built in by evolution into our brains. And then we start observing data through our senses, and that prior keeps getting updated, turns into the next posterior, and so on. And so that's the model of how we might be learning over our lifetime. And I think one of the most important things in a good Bayesian approach to modeling is to be flexible enough and to allow for updating of the prior as you get more information. So your prior should not be too dogmatic. You should allow for the possibility of many different things.
Thank you very much.
Great.
I think if we had the attendees had just their webcam and microphone on, we were hearing them clapping for you for a really nice and great talk and really nice question answering session. And we were here for about 47 minutes question answering. It's really hard. Thank you for joining us and for presenting in our summer school. And I hope that we can have you again in our next events.
Great. Thank you very much. I really, really enjoyed presenting. I've been very happy to be able to present at the IPM, and hopefully the students got a lot out of it. And I wish everybody luck in their, research in machine learning and AI.
Thank you so much.
And thanks to the organizers. Thanks, Mohsen. Thanks.
You're welcome. Thank you, and bye.
Bye.
Okay.